Hello friends, welcome back to my YouTube channel MS Maths. In this video, we are going to discuss about Henny-Borel theorem. So basically, Henny-Borel theorem is related to the sub-interval and interval. So basically, we are talking about the Measure integration. So in the measure integration, we will discuss some properties of intervals. So basically, if A is a complete set in R, A is complete set means that every Cauchy sequence is convergent in this set, okay, or every convergent sequence is Cauchy sequence. So this is a complete complete set in R, complete set in R. Basically, that it is R. Then A subset of I say some union of intervals. So basically, this is some union of interval in. Okay, so union from 1 to infinity, where the set in are open interval. Okay, so this is basically the open interval. Then there exists a sub collection of these sets. And which type of sets are basically ji, and where I is belonging from 1 to p. Okay, some finite number of sets. So basically, this is the set that we have. A is basically complete in R, and which is nothing but the union of all 1 to p of all the sets ji is nothing but the subset of interval. So basically, this is the Henny-Borel interval. So basically, this is the interval, and this is the property of this interval. Now we have the theorem is that outer measure of an interval is its length. So basically, what is the length of, if I'm talking about the length of interval? So the length of interval means that if you have any interval in this way, that a minus ab, then the length is denoted by this L. Okay, L of I, or I say it is I, then it is nothing but b minus a, and obviously here b will be greater than a. So basically, it is the length of. So it says that the outer measure for this is nothing but the length of the interval. So we will prove the we will prove this, that outer measure, will find the value of outer measure. So basically, measure and outer measure is nothing but outer measure of some set A is nothing but the infimum of the all open sets, like length of all open sets F, where A contained in F. Okay, so this is all about the outer measure. This is known as outer measure, and this is the notation of outer measure. So we'll start with the interval. So if I say that the interval, we'll start the proof. Then when I is equals to a comma b is an interval, is closed interval and bounded. So basically, it is a closed and bounded. Now, for given epsilon greater than 0, an open set or an open interval. So what will be the open interval for this closed set is basically the a minus epsilon and a plus epsilon, such that where I is nothing but closed set of AB, subset of it is nothing but a minus epsilon and b plus epsilon. So now L is basically the length, taking the length of all the both the side. So the length of I, so the length of I is basically the length of a minus epsilon and a plus epsilon. So obviously, the length of, because it is a subset, or this will be the subset, then the length of I is less than equal to this. So basically, the length of I is less than equal, it will be less than equal for b. We can write in this way, that b plus epsilon and a minus epsilon, or here what will be the length. Okay, if we are going to find the length, it means that it will be basically b plus epsilon. So b plus epsilon, so the length is nothing but b plus epsilon minus of a minus epsilon. It means the length of I is nothing but b plus epsilon minus a plus epsilon. Then Taking the outer measure both the side. So if I'm going to take the outer measure of interval, this is basically less than, or length will be here, okay, length of interval will be here, then I, and here will be the, or we can write in this way that outer measure is nothing but the length. So the outer measure of I is nothing but length of, is less than equal, we can write in this way, less than equal the length of interval I is less than b minus a plus 2 epsilon. So if m star, it means outer measure of I is less than equal the interval, like length of the interval is less than b minus, we can write in this way, b minus, okay, yeah, so m star, yeah, we can write in this way that outer measure of I is less than b minus a plus 2 epsilon. Since we can write, since epsilon is arbitrary, so that outer measure is nothing but, we can write b minus a only. Let I is interval, that is a comma b, implies that there exists a countable collection of the open interval. Henny-Borel theorem says that countable collection of the open sets, or we can write in this way that open interval, then In, we can say that In is basically the all the intervals. So I is nothing but the subset of union of all the collection, or all the individual, the subsets of or subinterval. Hence, by Henny-Borel theorem. So Henny-Borel theorem says that there exists a finite subcollection, So basically it is Ji, and where I running from 1 to some p. And we have already discussed in our Henny-Borel theorem, it says that the I is subset of union of I is equals to 1 to p is Ji. It is the subset of union of 1 to infinite. It is basically the finite set, and it is infinite set, that is In. Now we can take the sum in this way, like sum of the length basically. So it is nothing but sum of I is equals to 1 to p of length. Okay, union is for the set. If I am going to take the length, then it will be the sum. So in the same manner, it is less than, or because it is the subset of this, then less than n is equals to 1 to infinite and length of In. Okay, now given, what is the given? That I is the interval, let A belongs to interval I1. So it means it is an open interval, so A1, B1, in such a way that A1 less than A less than B. It means A is belonging from I1, which is inside, or which is between A1 and B1. If B1 less than B, B1 less than some B, then it means there exists some I2. In this way, there's like that A2 B, such that B in between the B2 and A2. It means B2 is less than B is less than B2. Okay. Similarly, in this manner, you will have I3, it will be A3, B3, and you will have a C. So like C will be the, so yeah, in this way that some B, okay, yeah, like B is less than, in this way, B is less than B1, then we can write A2 less than B1 less than B2. And similar way, you can write in this way A3 less than A3 less than B2, A3 less than B2 less than B3. It means all these sets are connected to each other. Okay, all these sets are connected. Like in this way, you can see if it is A1, B1, then B2 is basically inside the, like between these, it is B2. Similarly, for B1 or like in such a way that B1 is between in this way, wait, yeah, A1 B1, and B1 is between A2, this is A2 and B2, and B2 is between some A3 and B3. So in this way that you can like partition, you can make the partitions. Okay, so now we'll have now again and so on for here and so on. Now come to the our previous point, that is the sum of I is equals to 1 to infinite the length of all the ji's intervals. So all the ji's interval is basically the length of all jp interval. So we are starting with the last point, that is because it is a finite element, because of like from 1 to p, it is from 1 to p, not infinite. So it will be length of jp plus length of jp minus 1 plus length of jp minus 2, and such a way that length of j2 plus length of j1. Okay, so it is basically the length of j1. Okay, so we will have the values of the length of all these interval, that we can say it is nothing but some element bp, or we can say that it is nothing but if ji is an interval, then it will be ai and bi. So the length of this ji is nothing but bi minus ai. So we can write here it is nothing but bp minus b and subscript p, a subscript p, plus we can write b p minus 1 minus a p minus 1, in such a way that we can write it is b2 minus a2 plus b1 minus a1. Okay, now here you will see all these things will be 0. Because of that, like if you will write in such a way that here will be some bp minus 2 minus ap minus 2, and you will have some elements in this way, that b like ap minus 1 or these all the things can be written in like using all these equation. Because of that, all the intervals are stuck in between, all the like all the terms are stuck in between two like points, so that we will write in such a way bp is one of the individual point, otherwise all the points will be a p minus ap minus 1, this will be 0. Okay, this will be 0. Similarly, minus a p minus 1 minus a, or basically no, this is bp minus 1, bp minus 1, and this is bp minus 2, then is like this will be also 0. And similarly in this way that a2 plus a2 minus b1, it will be 0, and here will be last will be a1. So basically you can see here, because this step is all about these things. Okay, this step is all about these things, because all the points are in between two other like to another point of the interval. So that's why we can make it 0. Now you can see here we were finding about the length. So basically it will be I is equals to 1 to p, length of all ji's interval is greater than this is the element, that is bp minus this is the element a1. Now it is nothing but last element and it is first element, so we can write it is b minus a. Okay, so it will be less than equal to or I equals to 1 to infinite, that the summation I equals to 1 to infinite or 1 to n, because now we are taking the interval in. Okay, or the original interval, that will be greater than the length of this will be this interval will be greater than, because of this gi's intervals are basically the subsets of these interval. So it will be the summation of I is equals to 1 to p, the length of all gi's is greater than b minus a. Now we can take the infimum of the length of I is equals to 1 to n, and this is the form, or this is the definition of the outer measure in the form of intervals. Basically, the outer measure have two definitions, like outer measure of A is nothing but the infimum of the length of all open sets where A contained in F. And similarly in the interval, so outer measure of A is nothing but, or it is basically the infimum of summation of I is equals to 1 to some infinite or some finite point n, like length of in. Okay, this is in the form of intervals. So here it is nothing but the outer measure. So outer measure of I interval is basically greater than equals to minus BA, that our theorem proved here, that we were proving about the outer measure of an interval is its length. Then it is all about the length of interval. It is nothing but the length of interval. So this is all about this thing. Now we can take the case number 2. So this is basically the case number 1, in this way that we have considered this thing, that it is basically the case number 1. Now we can proceed with the case number 2. Okay, so second, so case number 2, how can we proceed with that? Let I is an open set. In that way, that epsilon greater than 0, where A plus epsilon B minus epsilon is subset of I, is subset of some interval AB. Now taking outer measure for this, taking outer measure, then it is length of A, or basically length of the interval A minus epsilon, or I think this should be A plus, yeah, A plus epsilon and B minus epsilon, close interval, that is basically less than outer measure of I is less than the length of, outer measure is nothing but all about the length of this interval. So basically we can write in this way, the length of this particular interval is basically B minus epsilon minus A minus epsilon is less than outer measure of I, or is less than the length of this is nothing but B minus A. We can write B minus A minus 2 epsilon is less than M star I is basically less than I is less than B minus A. Now we can write in this way, if we find the value, or it is basically the arbitrary. Okay, so we can take it as B minus A less than outer measure of I less than B minus A. Now the thing is, outer measure is greater than B minus A and outer measure is less than B minus A. It strictly implies that the outer measure of I is nothing but the length of interval. It means we can write in this way, outer measure is nothing but the length of this interval. Okay, now we can take this third case. In that way we will have case number third. So case number third is all about the infinite interval. It means that let I be an interval, which is I be an infinite interval, that we can write I be an infinite interval. Okay, so we proceed with the three cases. First we have taken the closed interval, then open interval, and then infinite interval. Okay, so the length of this interval will be infinite. Okay, then a real number k which is greater than 0, there exists a closed, let basically, yeah, we are considering this. So let for a real number k greater than 0, there exists a closed finite interval, closed finite interval j, such that j is contained in I. So j is contained in I, and where the length of this j is basically k, where k is some real number belonging from real number. Now j is contained in I, it means the outer measure of I is less than equal the outer measure of j. Now we can see the outer measure of I is less than the length of j, which is nothing but k. Okay, which is nothing but the length of j is nothing but k. So hence inequality satisfies only when k is arbitrary. If k is arbitrary, then it will hold. Then it means k may be infinite for in this case though. So it is basically the outer measure will be equals to the length of the interval only. So this is all about the outer measure and Henny-Borel. Using the Henny-Borel theorem, we have proved it. So thanks for watching my video. Keep watching MH Maths, and for these types of video, follow my channel. You subscribe the channel, share with your friends. Like related to higher mathematics, you can get all the types of topics from here. So thanks for supporting me, and thanks for watching this video. Keep watching MS Maths. Thank you. Bye bye.